So next here, we're going to talk about solubility. So we're going to kind of carry through this idea of attractive forces and essentially how that drives something dissolving into another substance and forming a solution. And so, this is kind of our driving force. How much will dissolve? In chapter, 4, we did solutions in 221, but we didn't really focus so much on whether something was more or less soluble. We just focused on was it soluble or not. We had a solubility table for that. So now we're going to kind of discuss what goes into it and the fact that it's not just like yes, no, but some things you're able to dissolve more or less in a given solvent. And so, how much of our solute, how much of the stuff we're dissolving will we actually be able to dissolve into a given solvent, what we use to do the dissolving? Well, that's going to depend on these intermolecular forces. And so kind of the key thing, this is what it really boils down to right here, is that like dissolves like. And so nonpolar compounds, they're going to dissolve in nonpolar solvents. And polar compounds will dissolve in polar solvents. And the better they match up, the more polar the solute is, the more polar the solvent is, the more they're going to dissolve each other. And then on top of that, if you have something like a compound that can hydrogen bond, it's going to dissolve even more readily in a solvent that can also hydrogen bond. So it's not just polarity, but hydrogen bonding can come into play as well. And just the better that these intermolecular forces match up, the better it's going to dissolve, the more of it that you will be able to get to dissolve, because every solution has a saturation point where you can't dissolve any more stuff. And so we're just going to talk about, well, is it a larger amount or a lower amount to get to that point? And it just boils down to matching up these intermolecular forces. And so to start out, if we do an example here, we can ask a question like, which dissolves something like decane, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is non-polar. It's 10 carbons long. That's right, line drawings are back. Now you know how to use them. I'm going to use them a lot. So hopefully you're familiar with those. So what would dissolve this better? So we're going to kind of ask, what solvent should we use to dissolve decane? So our first option, 1, 2, 3, 4, 5, 6, is called hexane. And our second option, good old acetic acid. All right. That's what we're comparing here. And so this is a nonpolar compound. It's all carbons and hydrogens. That generally means nonpolar. We consider all those bonds to be nonpolar. Again, your book gets squirrely, but whatever. This is also a nonpolar substance, all carbons and hydrogens, but we have polarity here. We have polarity here, and then there's going to be a polar bond between the hydrogen and the oxygen. And it can hydrogen bond. So this is a polar compound with hydrogen bonding capability. But our solute, what we're trying to dissolve, doesn't have that. So these match up in intermolecular forces. Nonpolar, nonpolar. This is polar over here. Plus it hydrogen bonds. This is nonpolar. You can review the video on this stuff if need be. It's one nice thing about these videos. You can just kind of like scroll off the page, click again, give another look. You can also look over the line drawing video. But this is nonpolar, this is nonpolar, therefore this is our answer. That is our matching pair. Like dissolves like. Like dissolves like. Nonpolar dissolves nonpolar. Another example here. I'm going to erase this real quick. But another example we'll talk about is a little tricky twist on this. That's ionic compounds dissolving. And I think I showed this in my 221. But ion dipole interactions, remember we can have these happen. And so you've all seen salt dissolve in water. I literally made oatmeal this morning. I had to dissolve some salt in the water and boil it. So like, I know it works. I saw it happen today. But salt is an ionic compound. It has these ion attractions. Water is not ionic. It's a polar compound. but it will still dissolve an ion. So we have this kind of mixed interaction here that can happen as well. And so ion dipole interactions can also drive, something like water, which is polar, to dissolve ionic compounds, which are just salts. Now, this doesn't always work. There are some what we call insoluble salts. You might remember that from the previous chapter. It turns out they actually are a little bit soluble, just almost imperceptibly so. We'll talk about that more in 223, actually. And so what we see is that this ability to have ion dipole interactions, if those can overcome the ions interacting with each other, they're gonna lead to solubility. And so if we have something like NaCl into H2O, there it is, by the way, salt in this chapter, strikes again. Well, our salt is just you got a sodium plus, a Cl minus, sodium plus, a Cl minus. And this is all stacked in 3 dimensions. We'll actually talk about that in the solids chapter, which is chapter 12. And we'll talk about, so there'll be Cl's minuses going down here, and then NaCl, and coming out as well. It'll be like a cube. But we're gonna keep it simple, so I'm just gonna write one string. And so this could keep going. Now, the positive cation is attracted to the negative anion, opposite charges attract. Well, what happens is water comes in, right? And remember, this area right here is partially negative, partially positive, partially positive. Well, this will interact. Now, one water isn't going to do it. It takes a whole group of waters to have this interaction take place. And then for the anions, well, we just have the positive portion of the water interact. We have a bunch of waters team up, and they form what's called a solvation shell. And so what we get, I'll do a little arrow here to demonstrate. What we get is something like a cation, in this case the sodium plus ion, and it's going to be surrounded with waters that are oriented with the negative portion towards it. And it's more waters than I'm drawing, Whoops, there's only so much space on the board, but it is, it's a lot of waters. Lots of hands make light work, so on and so forth, that are having this occur. And it'll actually have a second layer around it. So water starts to kind of develop a semi-structure around these ions. And so you have the plus, cation doing this. And then you have the negatively charged anion, which is the opposite part of the water oriented towards it. And so these positive H's are attracted to the negative charge of the chloride. And so this is what drives the solubility of salts. Now, we're going to talk about this kind of more in the next chapter, but just an early heads up that if this ion-ion attraction is really strong, and we've talked about what that would mean. It would mean small ions with large charges. If that's a really strong attraction, you can't get enough waters around it to break it apart. And that's what gives you an insoluble salt. And that's more of a chapter 11 thing, but I always like to give you guys an early heads up. And so we get this, what's called solvation shell, these oriented waters that have seduced the ions away from each other. I mean, they never really, it's not like they were sharing electrons. They were always just stuck because of charges. Well, these waters can bring in enough countercharges to kind of pry them apart. As long as, this attraction isn't too strong. So, it's sort of a sum game. All right, and so what drives that is ion dipole interactions. And I'm going to need to make some space on the board to talk about the last thing here. We're going to talk about solubility of gases versus solids, just some general rules as we change temperatures and pressures. But the first thing you should look at is just like dissolves like. All right, so we'll be back in a second. I just got to erase, make some room here. We'll talk about the last part, and that'll be into this video. Okay, so we're going to look at gases versus solids. This is kind of the last piece of this topic. And so everything from before still holds. So like dissolves like, that underpins everything. That's a very key idea, polar, non-polar. But we can get gases to dissolve just like we can get solids to dissolve. Or you can also dissolve liquids and other liquids, but we're not going to worry about the rules for that. There are some key differences between dissolving solids and gases though. And you've seen gases dissolve. If you ever had a carbonated drink, that has CO2 dissolved in it, or there's some beers now that they use nitrogen as the carbon, so it's not carbonated, it's, I don't know, nitrogenated, I'm not sure what the term is, but to give it bubbles. Apparently they don't burn your throat as much or something, I don't know. But you get a gas to dissolve into a solution. So that, we've all seen that, I think. And same with solids. You know, if you ever dissolve sugar in water or salt in water, you've seen a solid dissolve into water. But there's some key differences in terms of how soluble these are going to be, specifically with respect to changing temperature or changing pressure. So if we heat a solution up, we will be able to increase how much solid will dissolve. The saturation point grows. As temperature goes up, saturation point goes up. We can put more solid into this. So we've done this in lab. We did this in 221. When you're doing the alum lab, you'd heat the solution up and then you would cool it down and then you'd start getting crystals forming. And, you know, unless you were a bad person and you know what you did so that your yield was bad, that's on you. Obviously it's not random luck, it's not skill, and it's none of that. It's just how good of a person you were. But as you would lower the temperature, solid would, we'd say, crash out of solution. You started seeing crystals form. Or again, you didn't. Maybe your neighbors, you saw your neighbors' crystals form, I don't know. But if we increase temperature of a solution with dissolved gases, the solubility goes down. Okay, so the opposite happens. So you got to be aware of what we're talking about here. Are we talking about dissolving a solid or a gas? Because it's a totally different set of rules. There's a thermodynamic explanation for all of this, which means that's next quarter's problem, not this one, but you just kind of remember what this means, and we'll circle back to it in a second too. If we increase pressure, you can't really compress solids into a solution. You know, they're already very compact. That's not going to help. But if you increase pressure on gases, you can push them in the solution. They will compress in the solution. And so if you think of trying to keep a beverage carbonated, both of these should make sense, because what do you want to do to keep a beverage carbonated? You keep it cold, so you keep the temperature low so the gas stays soluble. And the other thing you do is you tend to keep the cap on it. Because when you keep the cap on it, the vessel that it's in will pressurize, and that will help keep gases dissolved as well. If you keep it open, they'll just keep undissolving and going into the atmosphere. Or if anyone has ever seen like a soda stream machine, it just uses compressed CO2 and it compresses the vessel and gets CO2 to dissolve into the water, and then you have soda water. That's what it does. So it employs this trick with pressure to create soda water by dissolving more CO2 into the solution. And so whether we're dealing with a solid or a gas, you got to be careful. You got to take a step back and think, what is my solute? Is it a gas? Is it a solid? What can I do? Because the rules are either dead opposite or, you know, they're just completely unrelated. All right. Now there is one little equation here. So there's Henry's law. And so the concentration of gas that's dissolved into our solution. Now here's the great thing, like Henry really cashed in here. He got a law, he got an equation, and he got a constant all at once. I'm very jealous of this guy, I'm gonna be honest. I wish there was Joachim's law, with Joachim's constant and Joachim's equation. And if I could somehow fit two constants in there, I'd be just overjoyed. It'd be like Joachim's first constant and Joachim's second constant. Even if it's a zero, I don't care. I want that constant. All right. Anyway, Henry's law. So the concentration of a dissolved gas, and this is generally something like molarity, like moles per liter, something like that, or, you know, grams per milliliter, whatever the units are. Well, we use Henry's constant and the partial pressure of the gas. And so Henry's constant just converts to the units we want from pressure. And so all it's saying is, well, as pressure goes up, concentration goes up, because this isn't changing. This is just it's a constant. If pressure goes down, concentration goes down. So it's mathematically, it's just kind of specifying a little bit more than the general hand wavy. So you can use Henry's constant, you can actually solve some problems and get exact numbers. But I'm really more concerned with the general idea of this. All right, so intermolecular forces, they drive all this solubility stuff, like dissolves like. And then for thermodynamic reasons, just kind of physical property reasons, we can get some temperature and pressure differences between how solids dissolve and gases dissolve. And you don't have to understand why these differences occur right now. You just need to understand that they do occur, and you've observed this. You heat up a solution, you can get more solid to dissolve. You cool it down, it undissolves. If you ever made simple syrup, you've used this trick as well. Gases, anytime you try to keep a beverage that was already carbonated to stay carbonated, you've employed these tricks. So you've seen this before. And then there's a little bit of math we can throw in as well, but focus on that end first and really think about how intermolecular forces applies into this as well. All right, so we'll leave it there. We'll continue through the chapter with the next video.